Hello, it's Keith here, and this is lesson 6 of my multi-platform series of Z80 tutorials. Now, if you've been following my series recently, we've been having a look at using Tracker for music, and over the last lesson we also had a look at how to use Interrupt Mode 2 in the advanced series, and previously we've also looked at Interrupt Mode 1 as well. So if you've been following, you should understand now how both interrupt modes work, and you will have some understanding of how Tracker works. And today we're going to look at taking that a little bit further, because last time we used Tracker we were just using some fake interrupt handling to just delay the update of the music, whereas this time we want to actually create a proper interrupt handler that will, on a timed 50 Hz refresh, update the music so that it plays at the correct speed on all of our systems. Now, today we're going to cover the procedure a bit, but I'm actually going to provide you with an example code that I've written that will basically do all of the work of each individual platform for you, and will allow you to just create your own interrupt handler without worrying too much about how it actually has to work. Although today we will actually go into the details of what it's doing. I will show you how to use it, and I will show you some of the more advanced functionality it has with regards to I've mentioned in the past how to misuse the stack for fast reading and writing, and usually because the interrupt handler will write to the stack when it calls, this means you have to disable interrupt. But in limited cases, if you're careful, you can actually use the stack for fast reading and writing but keep interrupts enabled, and that's very important if you're on a system like the ZX Spectrum, where if you miss an interrupt it never fires again, or on the Amstrad CPC with raster interrupt changes or line level interrupt changes, where if you miss the interrupt and you're using the raster to change the screen colors like Chibi Akuma's does, if you've missed it, well, your color change will now occur in the wrong place. So in both those cases you really want to disable interrupts for the absolute minimum amount of time you can, and this more advanced interrupt handler with what I refer to as a shadow stack, which is an alternate stack pointer that is used only during the interrupt handler, will allow you to do that and will make your interrupt handling just as good, but will allow you to really have some flexibility when it comes to misusing the stack pointer. So anyway, let's have a start. Let's have a look at the code. So I'm not going to go into any real details of what Tracker is or does, but here's my sample code. We'll have a look at it later. Let's just compile it for starters. Now, I should point out first of all, I'm compiling in using Interrupt Mode 2. So let's just fire this up, and you can hear the music playing. If I stop the assembler, you'll see IM2 here because we're in Interrupt Mode 2. Well, why are we? Let's stop that. Why are we in Interrupt Mode 2? Well, a lot of the systems, the way that my default toolkit are set up, leave the ROM into bank 0, the first 16K of the Z80's addressable memory, and because Interrupt Mode 1 needs access to that, it's more convenient for me to use Interrupt Mode 2 for these examples, but we can very easily switch the interrupt mode we're working with. So anyway, that was the Amstrad, and today's example does work on virtually all of the other systems we're looking at. So for example, here's the Sam Coupe version, which will sound slightly odd because it's using emulation. And then you've got MSX here. And we've got ZX Spectrum as well, somewhere. So you can see that this works just fine on all these systems. So the first thing is that we've got an interrupt handler that works in a platform-independent way on all these systems, and also we've got an interrupt handler which we can very quickly switch between Interrupt Mode 2 and Interrupt Mode 1. And I'll just show you how easy it is. All I need to do is I disable this line here, recompile, and we are compiling for the CPC. And we just do call and 8000. And if I stop again, you can see now we're in Interrupt Mode 1. And that's all it takes for me to change the way this program works. So on systems like the Spectrum, where Interrupt Mode 1 isn't possible, or on systems like the Sam Coupe where it may not be preferable, we can use Interrupt Mode 2, but we can use Interrupt Mode 1 on the Enterprise and the CPC, where it's an option, and the MSX, of course. And all we need to do is change the one line, and the interrupt handler we're using is identical, so we really have the flexibility there. So let's have a little bit more look into detail of what this, how we actually use this interrupt handler that I've written. You will be able to, of course, to download all the source codes. Just go to my website, download the sources 7-zip, which has all of the stuff in my tutorials, and you're totally free to use this in any way in your own projects if you feel you wish to. Okay. So the first thing we have to do is, if we're going to use interrupt mode 2, we need to make sure there's about 512 bytes of space at this around 8,000 to 8,200. Now all of these tutorials that we're looking at today, all of these systems, the program will start at 8,000, so we're just creating a dummy block here of space that when we install the interrupt handler can be overwritten with the jump block that interrupt mode 2 needs. Now if you don't know what that jump block is and you don't know why 8,000 is important, please see my previous lesson, lesson A2, and that will show you how that works. Okay, so you can see we're installing the interrupt handler here, and then we're just dropping into an infinite loop here, and we've got some more code we're going to look at later, but we'll just skip over it for now because that's actually all that our program's going to do. The rest of the work is done by this bit here. So you can see we have a file we read in called the interrupt start, and this is the header chunk of data that handles the receiving the interrupt, backing up registers if required, switching to the shadow registers, because all of the examples today you'll be looking at, my interrupt handler by default assumes that it has total control of the shadow registers, but you're not going to need to use the normal registers, so it won't, unless you require it to, back up the shadow registers. It will assume it has them for itself, switch them in automatically. And so the start does all of that. The end undoes all of the work the start did. And then so in between, we just have this play command, which updates the music. This fast tick label is required by the Amstrad CPC. On the Amstrad CPC, there's actually, it's not a 50 Hz interrupt, it's a 300 Hz interrupt. And so all 6 times, 5 out of the 6 times, it will not run this command, it will jump straight to this fast tick. And so if you need your music to update 50 times, 50 Hz, but you need to use the 300 Hz for raster colors, for example, then you put your raster colors in here, you put your music in here, and everything will work just fine. So I've kind of I've maintained the support for the 300 Hz with this label, but maintained the 50 Hz speed for compatibility with the other systems. So that's what your basic interrupt handler block will look like. And then if you want to return to basic, all you need to do is uninstall the interrupt handler, which, where is it? I don't actually, because a lot of the systems can't return to basic, like the MSX cartridges. There's no basic to return to. So so interrupt handler uninstall here will take the interrupt handler away. If it was written to the firmware, it will be unwritten, and the original firmware interrupt handler will be restored. And if it's in interrupt mode 2, it will be switched back to interrupt mode 1, because to my knowledge, all of the computers you will see, all the computers I look at, are in interrupt mode 1 by default when the firmware is in control. So that will undo any work that the interrupt handler has done while your program was running, so that you can return to basic or use the firmware if you're using disk routines. That's quite important. Okay, so let's actually have a look at what the interrupt handler code does. And I warn you, it's quite complex, so brace yourselves. Well, first of all, let's have a look at some of the other options we've got. Now, you can see we've got a few extra options here. I've already mentioned this interrupt mode 2 option. There's the allow stack misuse function, which, as I've said before, you can misuse the stack pointer, pointing it to blocks of data, and then quickly read or quickly write those blocks of data. But usually this causes some quite significant problems with if interrupts fire, and your interrupt handler would cause that. But this will help protect it, and in most cases you can have the interrupts enabled even when you're misusing the stack. We'll look at it later, and I've got an example. Now, protect shadow registers. As I've said, the interrupt handler by default will switch to the shadow registers, but it's possible that your code actually needs those as well. So if your code does need those, you can enable this protect shadow registers function, and the shadow registers will also be protected. Now, in the case of Arcus Tracker, which is in our interrupt handler, can't work with just shadow registers. It actually needs all of them, and because this would ruin our program, we actually need to enable this need all registers function so that Arcus Tracker won't corrupt the basic registers. If our code needs the shadow registers as well, you just enable protect shadow registers, and then everything's protected. You can do absolutely whatever you want in your code and your interrupt handler with all of the registers if that's what you require. But of course, protecting more registers than you need to for the interrupt handler will waste a little bit of CPU power. So if you can avoid it, obviously protect as few registers as you can, just to save a little bit of time. So let's go into our interrupt handler and have a look at all of the code. So it's quite complex, but bear with me. So on the here's the install, which will put our interrupt handler in, replacing the firmware one. Now on the Amstrad CPC, the system firmware requires the shadow register BC to be a specific value, so we back it up here. You'll see there's a no operation here. What's that for? Well, I've put a bit of a trick in so that if you install the interrupts twice, there's self-modifying code, which will mean that the second time it will do nothing. And the reason for that is if you accidentally install the interrupt handler twice, then the second time it would back up the interrupt handler you'd already installed rather than the true firmware one. So this was a safety net just to stop you installing the interrupt handler twice. So once you've installed the interrupt handler, this no-op will be changed to a return. And so if you run it a second time, it will do literally nothing. So anyway, that's what this does. Now, if we're not using interrupt mode 2, then what we do is we put a jump in at our address hex 38, which is where the interrupt mode 1 interrupt handler resides. So we're just putting in a jump and then the address of the interrupt handler label. If we're in interrupt mode 2, then it's a bit more tricky. We put a jump at 8181 and then we fill the block 8000 to 8101 with the byte 81. If you don't know why, I'm not going to explain it again. Please look at my last tutorial on interrupt mode 2. If you don't care why, just trust me, that's what you do. So anyway, we then need to use the I register and we need to set that to 80, which we do with a rather strange decrement there because we know it will be 81 first. Then we turn interrupt mode 2 on and that will effectively make our interrupt ready. At this point then, we use this safety lock command which will toggle the interrupt on, and that's how we get things so that we're able to not accidentally run it twice. Now you'll notice by default interrupt uninstall just has a return at the start, and that's because if you uninstall the interrupt handler before you install it, you don't want to do anything. And again, this is the self-modifying code kicking in. So again, if interrupt mode 2 isn't enabled, then we need to put the firmware's jump back at 38 so that interrupt mode 1's normal interrupt handler is back in place. If we're in interrupt mode 2, we don't do anything. We didn't back up the 8000 range to be able to put it back. It's not really sensible to do so. So all we do in that case is just switch back to interrupt mode 1. If we're on the CPC, we restore our firmware interrupt handler. There's a 0 missing there, but it makes no difference at all. It doesn't matter. And then we jump back to the safety lock command here, and the safety lock will basically just toggles the return and the XOR so that the one that ran last time won't run next time. So there we go. So that's the install and the uninstall of interrupts. They look a bit complex, but as I said, if you don't understand them, you really don't particularly need to worry about them, because I'm hoping these will actually work on your systems without you understanding them, provided you're not doing a lot more complex things than the example I've shown today, or you're doing things that are really pushing the limits of what this code can do. So the interrupts start here. Now this is getting a bit tricky. I think at this point what I need to do is just briefly explain what this concept of stack misuse is, as I call it. There's probably other terms for it, but I tend to call it stack misuse because I think it describes what we're doing. Now I'm hoping you know this, but the stack pointer is designed as a temporary store for data within the system. Now, I've kind of created this notepad here, which is just my virtual stack, which we're going to use as an example. Now, whenever you write data to a stack, the stack pointer moves up 2 bytes, and then the data is loaded into position. Whenever you pop an item off the stack pointer moves down. So if we moved it down here, we would load off these 2 bytes. And what the effect of this is that if we change the stack pointer to point at, say, bitmap data of a sprite, we can then pop off in 2 byte chunks the bitmap data of that sprite. Or if we want to clear the screen very quickly, we can fill a register pair with zeros and just push over again. And the push and pop commands are super fast compared to all other data reading and writing commands. So if you want to read lots of data over again, or read data really, really quickly without it changing, then push and pop are really good for this. The problem with this means is because the stack pointer is used by our calls and our interrupt handler is effectively a call, then if you can't use any calls in your code, and if an interrupt call occurred while you had the stack pointing to sprite data, then something would get corrupted. Now, what my interrupt handler does is it's got what it refers to as a shadow stack, and what this is it's an alternate stack pointer. And when stack misuse protection is enabled, what happens, the first thing that happens when the interrupt handler calls is it backs up the current stack pointer address, which would be your bitmap data if you were messing with it, and then it loads in its own alternate stack pointer, which it knows is available for its interrupt handler. The last thing it will do is it will switch back to your stack pointer that was being used, say, for reading your bitmaps or clearing your screen, and then it will return back using a jump, so not a call. This is where the extra thing comes in. Now let's just imagine. Let's imagine we're about to read 2, 3, 4, 5 here. Okay. Now, as I've just described, because I'm using the shadow stack, the only data that will be written to the normal stack is the data of the first call to the interrupt handler, because there's nothing we can do about that. That's a function of the Z80. We've got no choice there. But so what my program relies on the assumption is that whenever you're reading data off the stack, you're reading it with DE. So let's presume at this point we've done a pop DE, and DE is 1, 2, 3, 4, because we've just done a pop, and the stack pointer is now pointing at 2, 3, 4, 5. But shock horror, our interrupt handler fires, and it overwrites 1, 2, 3, 4 with XXXX. Now XXXX would be the address of whatever command ran just before the interrupt fired, so that would be the return address. Now what my stack misuse protection code does is when the interrupt handler fires, the first thing it does is it takes the address that is on the top of the stack now, and it backs it up and it puts it on a jump command at the end of the stack pointer, at the end of the interrupt handler. Why does it use a jump? Well, a jump doesn't affect the stack, you see. And then the next thing it does, because it's relying on you using DE for your popping of data, so what it does is it pushes DE back on, because DE will be the last data that was written, and that is the data that was just overwritten by the calling address. So now if you were reading data, everything will be back the way it was, and the only thing you need to make sure is true is that DE contains the first thing that could be possibly overwritten. We'll have a look at that later, but you need to make sure DE is initialized to contain the first data that could be overwritten before the interrupts are enabled. Now if you're writing, it's even easier. Now all of this popping, all of this DE thing will happen, but that doesn't really matter to you. The important thing is that if we were filling, let's say the stack pointer was all the way down here, and we were overwriting this data with zeros. So we were about to write some data to this line here, for example, but then our interrupt handler fires. Well, what happens is this line would be corrupted. Well, we were about to overwrite it anyway, so really we don't care. Now, you would have, for a few seconds, a bite of corruption there, but when the interrupt handler returns, everything carries on normally. So the only possible risk is that a few bytes of screen memory or whatever you were about to overwrite were temporarily corrupted. And the only time this is dangerous is if you assume that, let's say you had your screen memory here, and you were going to fill it all in with ones, but let's say just above the screen memory was some actual code. I can't remember any proper code. C9's return, I think. So you were filling with zeros here, and you're filling with zeros here, and then you're filling with zeros here. But then if when you've just filled the last byte, the interrupt handler happened to fire at that exact point, that's the only time it would cause a problem, because what would happen is it would move the stack pointer up one, and then it would overwrite your code. And so it will only ever use a maximum of 1 byte pair because of this shadow stack. But if it fires at the last possible moment, then it would overwrite something before it. And if that's important code, that's going to corrupt something. So when you're writing with the shadow stack, the important thing to do is just disable interrupts one command before the last command. Don't do your last push and then disable interrupts, because when if the interrupts fire after that last push, then you would actually corrupt some legitimate data if you're not very careful. So that's probably very confusing, very wordy. I apologize for that, but I just wanted to explain that. I have some examples to show you how it works, but I thought it was important you at least had a sort of verbal description of it, so that when you saw the code and what it was doing, you understood the complexity. So let's take a look. So what are we doing first? Well, the first thing we need to do is we need to get the calling address off the stack. If stack, all of this code here is relating to this stack misuse allowance. So the first thing we need to do is we need to get the return address off the stack somewhere. Now, we can't corrupt any of our registers when we're doing it. So if we're allowed to use shadow registers, then we switch the shadow registers in. If we're not, then we use self-modifying code, because remember, we can't use the stack, and we can't change the stack pointer yet because we need to actually do a pop off it. So what we do is we either back up HL into using self-modifying code, or switch to the shadow registers. Then we pop the return address off the stack. Now we put our return address in, use self-modifying code, and this is the jump label I mentioned earlier. So we don't do a return because we don't want to mess with the stack. So we actually do a jump here. And that's what that does. And so next what we do is we either fix HL using that self-modifying code, or switch in our regular registers. Well, why are we switching in our regular registers? Well, because I mentioned we've got the calling address back off the stack, but it's still there. And if we were using the stack for reading data, we might have just corrupted some of our sprite, and that's not going to be good. So what we do, as I've said before, we're relying on only the register pair DE being used for reading here. And so what we do is we push it back onto the stack, and so that, if the user is using this code correctly, will contain the bytes that should be in the place that the call of the interrupt handler corrupted. So that push DE should fix everything. Sorry, I made a mistake earlier. I said here this was the shadow stack. I'm wrong. That's actually backing up the correct stack. So this is the real stack that will be restored when the interrupt handler ends here. Actually, it's here that the shadow stack is installed. So this is now using the alternate stack that is totally exclusive to our interrupt handler, so that the interrupt handler can do what it needs without worrying about corrupting anything on the other stack. So now what we're going to do, if we need all of the registers, then we back all of the normal ones up by pushing them, which of course will go on that shadow stack. Then we switch to our shadow registers. If we also need the shadow registers backing up, then we do that too. Now we've got some platform-specific code, but it's relatively easy. On the enterprise, we have to send a command to tell the interrupt that we've dealt with it, otherwise it will fire again. So that's that. On the CPC, the interrupt happened 6 times more often than the other systems. So all of this does is it reads in and checks if the screen has just completed a full refresh, and if it hasn't, then it jumps to the fast tick, meaning that the next bit won't happen. So the next bit only happens once every full screen refresh, which is 50 Hertz, the same as on the other systems. And then finally, on the MSX, we need to read in the status register of the graphics system, because if we don't, again, the interrupt will keep on firing and everything would run super fast. So at the point we've got here, well, there's no more commands, and the reason for that is because if you look at our example, which I've lost, if you look at our example, well, that's where our real code starts. You see, we're kind of embedded between the start and the end. And then the end is just the opposite, very simple compared to the start. So all we do is we restore the protected shadow registers if we were protecting the shadow registers, and then we restore the regular registers if we were protecting them. If we're using stack misuse, we restore the proper stack, we turn interrupts back on, and then we jump rather than return so that we don't damage the stack back to the address using self-modified code, and that's it. It's very complex what it's doing conceptually, but if you look at the actual command and you understand what it's doing and why it's doing it, it's actually pretty easy, relatively speaking. So anyway, now let's have a look at, I've got a little shadow stack example here. It's not great, I apologise for it, but it'll have to do because I really didn't want to spend hours and hours writing complex examples. So let's just have a look at what we've got here. So what we're going to do is we're going to fill the top line of the CPC screen, or not quite all of it, so that we can see the corruption if it occurs. We're going to fill the top line here by using pushes. And then what we're going to do next is we're going to pop the line below using the stack for popping, and then we're going to write to the line below that with the data we just popped, and this will effectively copy a line to the line below. And so what we would expect to see if the stack isn't protected is we will see corruption in the data that was being read, and also we may see corruption at the start or at the end of the lines that were written and read, depending on when that stack pointer fired. So, okay, well, let's have a go at this, shall we? So let's take off our stack misuse protection, and let's turn off our infinite loop. And you can see we got quite a mess there. And as you can see, I'm sure there's lots of corruption there, and that's because what's happened is the interrupt handler is fired. The first thing the interrupt handler does is push all of the registers it needs to back up onto the stack, and so wherever the stack was, in this case the screen memory, has been filled with all of those pushed data, which looks like corruption to us. So obviously we got quite a big problem there. So yeah, we're not doing very well there. So let's reset that, and let's allow our stack misuse here. Let's just put some slash symbols here. So it's not very clear because it's so small, but I've just zoomed in on it here, and you can see that the slashes have actually been turned at the top to vertical lines, and the reason for that is because the second pixel down, the second line down, has been copied to the third line. As I say, I could have made this example copy huge blocks, but I really didn't want to waste the time. I've got much better things to be doing than writing silly examples, so please bear with me on that. But anyway, so the top line, the yellow line, was just done with pushes to fast write, and the second line was read with pops and then plotted to the third line. So if any corruption would have occurred, this yellow line would have been corrupt, and this middle line would have got more and more corrupt. But as you could see, there was no corruption, and that's because even though interrupts were firing at random points during the writing, the shadow stack was protecting the pops and pushes, and meaning that no data was changed. But as I say, there are some restrictions, and so let's show you what happens if we fail in those restrictions. So let's rem out our DI here, and let's put it in here. Now you see that last line is kind of blinking there occasionally. Well, what's happening there? Well, I'll explain. Now this is the last push we intended to do, but an extra one is happening at this point if the interrupt fires at this point. And the reason I've put in this rather strange random code here to fill DE with random data is so that because our shadow stack is still replacing the push, you can see it's quite often yellow, which is what the DE contained. But if random data fires, then we actually get corruption appear there. So as I say, we need to make sure really that we disable interrupts before the last push, so that data that's outside of the range we were planning to fill isn't corrupted. And so that's quite important. And then the other one is, in this case, you'll notice I'm disabling interrupts here, loading in the stack pointer we want to write to, and then I'm doing a push, a pop and a push again. And the reason I'm doing this is to preload the DE with the correct values of the first item that the stack pointer is pointing to, so that if the interrupt handler immediately fires, it won't corrupt that data we were about to read before DE contains the data. And so what happens if we do that wrong? Well, I'll show you here. So if we just take out these two here, we're now not preloading that first value before we turn interrupts on. And you can see, if we take a print screen here, and again we can see here that the first 2 bytes that we were about to read will get corrupted if the interrupt handler fires before we've got the first data popped off there. It won't happen very often, but of course it will happen. And because if this is data in a bitmap sprite, then every time it happens it will get worse and worse and worse. So you will find all of these, your sprites will all start getting randomly corrupted if you're using, if you're not using this protection correctly. Now, I just do want to explain something quite curious about disable interrupts and enable interrupts. Now, you'll see why. You see these no ops I've put here. Well, you're probably thinking, well, why are they there? Well, I've put all these no ops here to make the situation basically worse. These ones were just used for some test code as well. But if I take these out, you will actually see this works without corruption. And this is something that's okay. So the music is now playing, and you can see there's no corruption. And this is something I've not really explained before, but it's something very interesting about disable interrupts and enable interrupts. Okay, so here we've got the Zilog guide to the Z80, which, as I've said before, I think you really want to get, because there are times if you're really going to get into this, you want to know the facts. And so you'll see here with the disable interrupt command, get rid of that, it says this instruction disables the maskable interrupt during its execution. Okay, but on enable interrupts, it says during the execution of this instruction and the following instruction, maskable interrupts are disabled. And so what this means is, rather oddly, this will work fine, because when the interrupts cannot occur during this command. They can't occur because they're still disabled, and they actually can't occur during this command either until this command has run. So provided there are no commands in between, you don't need to do this preload of DE, and everything will work fine, because the interrupts cannot fire before this pop DE occurs in this layout. And that's something that's very important to understand. And if you're really trying to squeeze everything out of the system and make things as fast as you can, that's something you can do. And I've got a really good example of this here. So let's have a look at this example here. Well, what is it? Okay, well, if you look here, what we're doing is we're disabling interrupts here. So interrupts are turned off, and as I said, interrupts are turned off the second you do this DI command. Actually, we can even prove that. So we're doing disable. We're going to back up the stack pointer, turn off interrupts, set the stack pointer to 0, which is a bit odd, and that's because we don't want interrupts to happen at 0. We're going to load BC with FFFF. We're going to wait until BC hits 0, which is going to take a long time. And the reason we're doing that is because we can be pretty certain an interrupt should have occurred during that time. So this is just a really long delay so that an interrupt is waiting for us. Now, when we get to the end of that, we're going to turn interrupts back on. And the question's going to be, when the interrupt handler fires, is the stack pointer 0, or is the stack pointer our normal stack, which is around the bottom of the screen area memory? And so here we've got a no-op command here. And so what I'm expecting to happen is that actually the stack pointer will be pointing to 0, because that no-op, because while, as I said before, the enable interrupts, the interrupt handler can't fire during the enable interrupt command, but it can fire between the no-op command and the loading of the proper stack pointer. So let me prove that. So we do call and 8. Slow down there. So we do call and 8000. So here's our execution. We've just got to the enable interrupts. You'll see our stack pointer is still 0 here. If I press F7 to step forwards 1. Now interrupts are now enabled, but remember it will only occur after the no-op, because of it won't allow the interrupt until after the command has occurred. So if I press F7 again, we've immediately jumped to our interrupt handler, and you can see that the stack pointer is now FFFE, which is 2 bytes below 0. So we never got to our returning of the stack pointer there before the interrupt handler fired, which isn't what we wanted in this example. Now, it hasn't caused a problem, but if that was important data there just below the fake stack pointer, that would have caused a problem. So let's take the no-op out now, and let's run this example again. Okay. So we're now at our stack point. We're now at our enable interrupts command. The interrupts are turned back on. The stack pointer command is now about to fill in the stack, and you can see we've now done the jump. But if you look at the stack pointer is now correct. So despite the rather misleading tick in the interrupts thing, the interrupt physically could not fire on the Z80 until after the command following the enable interrupts. And this does allow you to be quite tricky with regards to in Chibiakumas, I had some code that before I had the shadow stack, I was doing very short enablings of the proper stack pointer so that the interrupts could fire, because I knew that I'd miss them otherwise and it would cause problems. And what I was doing was this: I was turning interrupts on, loading the proper stack pointer, and then immediately turning them off again, knowing that interrupts couldn't fire at this point, could fire at this point, so would have to if they were ever going to fire, and then turning them off again so that I could get on with the work I really needed to do. Quite funnily, this worked perfectly on the real Amstrad CPC, worked perfectly on WinApe, but I was trying to play it on my Nintendo DS emulator, and it was corrupting everything. And it was obvious that the way the DS emulator was emulating the Z80, it wasn't obeying this rule that the interrupts enable the command after the enable interrupts command. So I say something quite odd there. But as I've said, as we've just looked, because we've seen this in the Zilog manual, this isn't some Amstrad CPC thing. This isn't some MSX thing. This is gospel according to the Z80. So if you're using a true Z80, you should be able to rely on that it's working like this. So anyway, so there we go. We've had a look at our interrupt handler again. We've really covered, I think, all that we're ever going to cover on interrupts now. If you don't know how to do it now, you're never going to be able to do it. So I think we've really gone over all the interrupts. I've shown you how to do the shadow stack for your stack misuse. We've discussed what stack misuse does. We've done interrupt mode 1, we've done interrupt mode 2. We've learned how to make music timed on those interrupts. So I think we can call interrupts done now. So I hope you've enjoyed this lesson, and I'll link in the other lessons relating to interrupts if you want to see more on those. I hope you'll follow me, and we're going to carry on because we're nowhere near done. We're going to move on to some graphics work next week. We've done a little bit to text before, but we're always using the firmware. We're sick of the firmware. We're going off track, and we're going to do it ourselves this time. So we're going to go straight to the graphics hardware, and we're going to send data to the graphics hardware. So please follow me, and we'll learn about that. And we're going to do it on all of the systems as well. We're not just messing around on the Amstrad CPC. We're even going to be doing bitmaps on the TIE calculator. So I hope I'll see you then. Thanks for watching, and goodbye.